Okay, welcome back, guys. We're going to continue our discussion of equilibria. And to do that, we are going to start with defining a value called the reaction quotient. Okay, the reaction quotient. And this is a useful value to define. And importantly, this is not at equilibria. Okay, so the reaction quotient is something that's defined not at equilibrium. So if you have a reaction, our favorite generalized reaction, AA plus BB goes to CC plus DD, we define the reaction quotient as the product of the products raised to their respective stoichiometric values okay? And you might be thinking to yourself, wait a minute, this looks just like K. This looks exactly like the equilibrium constant Kc, right? That's true, it looks exactly the same. However, we must remember that this is defined as not at equilibrium, okay? So you can compute the same reaction quotient throughout the entire reaction process, even if it's not at equilibrium. And when it's not at equilibrium, you call this quotient the reaction quotient. At equilibrium, it's called the equilibrium constant. And you can also define QP for gaseous reactions, which is the product of the partial pressures of the products divided by the product of the partial pressures of the reactants raised to their stoichiometric coefficients. Okay, and these two can be calculated. At any point in the reaction. Okay, can be calculated at any point in the reaction, not just at the equilibrium like Kc or Kp. Okay, so this can be calculated at any point, and I guess you might be asking yourself, why would you calculate this at any point other than the equilibrium? Well, there's a very good reason for it. Q, it turns out, the reaction quotient, tells you about the progress of the reaction. Okay, so you can tell the progress of the reaction by looking at the value of Q and comparing it with the value of K. So if you imagine Q is equal to basically products over reactants. Okay, so at the very beginning, at time t equals 0, products is equal to 0, right? So then at the t equals 0, Q must equal 0, right? And if you look at time t equal infinity, we'll say, okay, at t equal infinity, basically there are no reactants left, so the reactants are equal to 0, and basically dividing by 0 is undefined, but it tends toward infinity. Okay, so that means that Q tends toward infinity as t approaches infinity. Okay, so the smaller the amount of reactants that's there, the larger the value of Q. So there is some range of Q between 0 and infinity for a reaction starting and a reaction going to completion, or going beyond the equilibrium. Okay, let's make one more definition. At equilibrium, so okay, at equilibrium, QC is equal to KC. Okay, QC is equal to KC at equilibrium. So if you imagine, or let's actually draw this out. Oops. Whew, I need to get better at drawing vertical lines, that's for sure. Okay, so if I write on this axis basically Q or K, that's the y-axis, and on the x-axis I'm going to do concentrations. Okay, let's do this for the generalized reaction. A goes to B. Okay, A goes to B. Q is equal to B over A. And let's say that K is equal to 1.45. Okay. So let's write out some points on here. 0.5, 1.0, 1.5, 2.0, etc. So K is at 1.45, so it's somewhere around here. Okay, so that's K. Okay. And then let's write out some concentrations here. So if we have, oh my goodness. Can I go back? Oh, I can. Okay, sweet. So if I have some concentrations here, for example, I'll do the concentration of A, and underneath it, I'll do the concentration of B. So if we start out with 1.00 moles of A, we have 0 moles of B, and we'll go to 75, 50, 25, and 0. So that would be 0.75, this would be 0.5, 0.25, and 0. This would be 0.25, this would be 0.50, this would be 0.75, and this would be 1.00. Okay, so those are the different concentrations. Okay, at the low end here, since Q is equal to B over A, since B is quite small here and A is quite large, we're going to have a small Q. Okay, so it's going to look something like this. And I think I'm crossing at the wrong point here, so I'm going to try that again. Looks something like this. Yeah, that's a little better. Okay, so at this point in the reaction, we have A going towards B. Okay, it's not really at equilibrium at this point. We're just making more and more products. And this is the region of the graph where Q is less than K. Okay, so when Q is less than K, the reaction tends towards the products. Okay. This is the point where it crosses the equilibrium line, and that's at equilibrium. If we have concentrations that are greater than that, okay, so say we have B value concentrations that are much larger than A, then we can keep going up this curve. And in this case, when we calculate Q, it's much greater than K, and that means that the reaction is going the other way around. The product, in this case, is being converted into the reactant, A. And when that happens, when Q is greater than K, the reaction tends towards the reactants. Okay? Okay. So when Q is greater than K, the reaction tends towards the reactants. When Q is less than K, the reaction tends towards the products. When Q is equal to K, nothing changes. It's at equilibrium. Okay? So that's why Q, or calculating Q for any specific point in the reaction, is very useful. It tells you where you are within the reaction, and it tells you how close or far you are from equilibrium. Okay? So that's Q. Let's go into a little bit more detail on how to find equilibrium concentrations. Okay? Okay, let's go into more detail on this and maybe do some more difficult problems. Okay, so there's a few different cases here. So the first case is if you are given all but one equilibrium concentration, Nk. Okay, if you're given all of this information, this is how you calculate the equilibrium concentrations. For example, let's do it as an example because I find that those are a lot easier. If we have COF2 gas being converted or dissociating into carbon dioxide gas and CF4 gas, okay, and we're given a Kc value of 2.00. We're given some equilibrium concentrations. Okay, so we're given COF2 equilibrium concentration and CF4 equilibrium concentration. The question is, can we calculate the concentration, can we calculate the equilibrium concentration of CO2? Okay, now the way that we start this is we start with our Kc expression. So Kc is equal to products, so CO2 times CF4 divided by the concentration of COF2 squared. Okay, so we have all of these equilibrium concentrations here. All we have to do is actually just solve for the CO2, which is quite easy. So we have then CO2 is equal to, I'm just going to multiply both sides of the equation by COF2 over CF4 squared. Okay, this cancels out here and leaves us with CO2 on one side, and we have Kc times COF2 squared divided by CF4. Okay, and we can directly calculate the concentration of CO2 by plugging in those numbers. So we have 2.00 multiplied by 0.255 squared divided by 0.118. And that ends up equaling 1.10 molar. Okay. In this case, we can include the units here. So usually with equilibrium constants, we don't include the unit. But in this case, when we're calculating a concentration, it's a good idea to include the units. Okay, so we get rid of one of those, and we get rid of the bottom, and we're left with molarity units. Okay, so 1.10 molar is is of CO2. Okay, so that's pretty straightforward. The first case, when you're given all but one equilibrium constant, and you're given the equilibrium constant value. In the second case, what if you're given the equilibrium constant and you're given initial concentrations? You're given the equilibrium constant and equilibrium or initial concentrations. How do you solve for the equilibrium concentrations? This is much more realistic. Okay, this is exactly what you would see in real life. Much more likely to see in real life than the first case. Okay, so if you have, let's do our general reaction. A gas goes to 2B gas. Okay, nice reaction there. If we have concentration, the initial concentration of A is equal to 1.0 molar. The initial concentration of B is equal to 0.0 molar. At the initial point, Q is equal to 0. So reaction must proceed to the right. Okay, so the reaction must proceed towards the reactants. Okay, so we're going to set up an ice table here. Okay, so we have initial change. Well, let's make that a little bigger. Initial change and equilibria. Then we have the concentration of A and the concentration of B. Okay, initial concentration of A is 1.0. Initial concentration of B is 0.0. Now here comes the tricky part. I don't know any equilibrium concentrations, so I have no idea how much A or B are going to change with in the change step. Okay, so I don't know the exact value, but I can represent this as a variable. So I'm going to say that A decreases by a value of negative x. Okay, and therefore if A decreases by x, that means that B, due to the stoichiometry of the problem, B must increase by 2x. Okay, so for every 1 x of A that you take away, you must create 2 x's of B. Okay, and then at equilibrium we have 1.0 minus x, and we have B is 2x. So the equilibrium concentration of A is equal to 1.0 minus x, and the equilibrium concentration of B is equal to 2x. Okay. Now, if we plug this into K, K is equal to B squared divided by A. Right? For this reaction, that's what K is equal to. Now we can just plug in these values here. So we have 2x squared divided by 1.0 minus x. And I'm not sure if I wrote this up here, but I didn't. I'm sorry. K for this is equal to 0.33. So we're just using the same generalized equation as before. Okay, so we can set this equal to 0.33. Okay, we can take this and we can simplify it a little bit. We can write this as 4x squared divided by 1.0 minus x is equal to 0.33. Now I'm going to pull this over to the other side, and you'll see why in just a little bit. Okay, so I have 4x squared is equal to 0.33 times 1.0 minus x. Okay, starting to look a little familiar. Now I'm going to pull the x squared over to the other side as well. So I end up with 0 is equal to 0.33 minus 0.33 times x minus 4x squared. What is this? What is this? What type of equation is this? This is a quadratic equation. And if you recall from above, we want to know what x is. If we know what the value of x is, we can figure out exactly what the equilibrium concentrations of both of these reactants and products are. We don't know the value of x. We want to solve for x. And since this is a quadratic equation, we have a very handy formula for calculating the value or the solution of this quadratic equation. I want you guys to think all the way back to your algebra courses. You remember? We learned a song. I learned a song at least. Hopefully you learned a song as well. That gives you the value or the solution. Wow, this is really bad writing. that gives you the solution to any quadratic formula or any quadratic equation. It's called the quadratic formula. And I'll sing the song for you. I think, what is it attuned to? I can't think of the tune. Anyway, the song goes, x equals negative b, plus or minus square root, b squared minus 4ac, b squared minus 4ac over 2a, Okay, this is the quadratic formula song, and I have remembered the quadratic formula for, 16 years. I've remembered the quadratic formula for 16 years because I have it in my head to that tune. I know it might sound really stupid, but really it's the one thing that has helped me remember this for so long. Okay, now these B's and A's and C's in here are given as the prefactors for each of these terms within the quadratic formula. Okay, and usually it's written as excuse me. So you write the x squared first, and then you write the x, and then you write the non-x equals 0. That's how you usually write the quadratic equation. And then you can write the prefactors as a, b, and c. Okay, so a in this case is equal to -4, b is equal to -0.33, and c is equal to 0.33. Okay, and you can plug those guys up into this equation up here, and you're going to get two answers. Okay, two answers. You can either get the case where you have the plus, or you have the case where you get the minus. Okay, so I like to call these x plus and x minus. I like to write them a little bit better than that too. X plus and x minus. Okay, so we have x plus is equal to -b, which is 0.33 negative, and I'm going to take this as plus the square root of -0.33 squared minus 4 times a, -4 times c, 0.33 divided by 2 times -4. Okay, and that ends up equaling, let's see, where is this? If you calculate it all the way through, sorry, I have it in my notes somewhere. Oh yeah, you end up with, here it is, -0.331. Sorry about that noise. My kids are doing something mischievous. They usually are. Okay, so that's the first value for x plus. Now we can find the x minus, okay? So this is just -0.33. And this time I'm going to say minus the square root of -0.33 squared minus 4 times -4 times 0.33 divided by 2 times a. Oops. Okay, and this ends up equaling plus 0.249. Now, in the case of up here, since we have so we have two values here, we have -0.33 and we have positive 0.24. We can't have two changes, so which one is true and which one is not true? If we look up at the top and we see that in this case we have 2 times x adding into b, and if x is a negative number, that means that we're actually taking away 2 times x from b. Since b is already at 0, this is impossible. Okay, so this is impossible. We cannot have a negative number here, and it's said to be unphysical. Okay, it's an unphysical answer, and so there's only one answer that fits, that makes sense, and it's 0.249. So in this case, x is equal to 0.249. Okay. And so because of that, the concentration, we can now calculate the concentrations at equilibria for A, which is just 1.0 minus x, which is equal to 0.75. And we can calculate the B equilibrium as 2 times x, which is equal to 0.50. Okay? There is another procedure, or more procedures. That's my daughter Hazel screaming for something. I'm not sure what. Yeah, me too, Hazel. Me too. There are more procedures and examples of this on page 696. Okay, so I recommend that you guys go through that, or go through those examples. I want mommy. I want mommy too. I don't know if you guys can even hear that. I'm pretty sure you can. Anyway, I'm sorry. Yeah, some days you win, some days you don't. Anyway, so there are some procedures and examples of this on page 696. I highly recommend that you go through those examples. They will vastly help you understand this process. Okay, let's stop there for the rest of this period. I hope you guys have a great Wednesday, and I will talk to you later. Take care.